Which one of the following compounds is an alkyne? To answer this question, we must know the formula of an alkyne. The formula of an alkyne is CnH2n minus 2. So we're looking for a compound that has a molecular formula that follows that CnH2n minus 2. And if we go through our options here, we can see that option B is our correct option. Question 1.2. Which one of the following is a functional isomer of ethyl propanoate? Okay, so a functional isomer, of course, we know is molecules that have the same molecular formula but different functional groups. So the functional isomer of an ester, so ethyl propanoate is an ester. So the functional isomer is going to be a carboxylic acid. So we're looking for a carboxylic acid. In other words, we're looking for something that has COO in it, COOH. Also, to help us along, if we think about ethyl ethanoate, ethyl has two carbons rather. So ethyl, 2 carbons. Propanoate, coming from the word propanoic acid, that has 3 carbons. And so we are looking for a carboxylic acid that has 5 carbons in total. So if you go through our options, A is not our option, B, so we have C or D. If you look at C, C has 1, 2, 3, 4, 5. D has 1, 2, 3, 4, 5, 6. So the option we're going to choose is option C. Now moving on to question 1.3. For which one of the following pairs of compounds will X have a higher boiling point than Y? So we're going to go through the options A, B, C, and D. If you're comparing A, you have CH3CH, then a bracket. The bracket tells me that it's a branch. And you compare it to Y, Y has no branch. So A, because X has a branch, it's not going to have a higher boiling point. So A is out. If you consider B, B is CH3CH3, so it's a short chain. Y is CH3CH2CH3, so B is also out because it's a shorter chain. And we know that for alkanes, the length of the chain, the molecular weight as well, it has an impact on the melting and boiling point. The longer the chain, the larger the molecular weight, the higher the boiling point. Let's look at C. So C is CH3, CH2, CH2, CH3, so that's an alkane. If you look at Y, you have CH3, CH2, COCH3. So if you're looking at the compounds now, they are different homologous series, and so they're going to have different intermolecular forces. X is an alkane, and so X is going to have London forces, so London forces or van der Waals forces. Y, because of that oxygen, is going to have dipole forces. And we know that dipole is going to be stronger than London, so Y is still going to have a higher boiling point. So C is out as well. So that means the option must be D, and let's just go through it. If you look at D, you have CH3COOH. That is a carboxylic acid. And we know carboxylic acids have 2 hydrogen bonds. Whereas if you look at Y, Y has OH, which means it's just an alcohol. Alcohol has 1 hydrogen bond. So carboxylic acids have 2 hydrogen bonds, which makes the intermolecular forces stronger, which makes the melting and boiling point higher. So the answer here is D. Question 1.4. Ethanol can be converted into other carbon-containing compounds using the reactions shown in the flow chart below. Okay, compounds P and Q are. Okay, so I'm looking at ethanol. So ethanol in reaction 1 is being reacted with H2SO4. So I'm thinking of what is the function generally of H2SO4. H2SO4 is generally used for dehydrating. So it's for removing for removing water. So if you have ethanol, right, and you are removing H2O, you are breaking that OH and you are taking a hydrogen away. So that ethanol is going to become an alkene. And so ethanol with the H2SO4 is going to become ethene. So compound P is going to be ethene. So B and D are out. Now we just need to look at what's going to happen to that ethene. So you have ethene and it's going to react with HBr. So in other words, you have this ethene compound like this, and you are adding HBr. So HBr. That the first thing that's going to occur here is that double bond is going to break, right? So you're going to have a single bond here. Then a hydrogen is going to be added. So you're going to add a hydrogen somewhere, and then the bromine is going to be added. So you basically going to have an alkane, or rather a haloalkane. And the name of this haloalkane is bromoethane. So the answer that we're going to go with here for 1.4 is A. Now 1.5 says, a piece of magnesium ribbon reacts with excess hydrochloric acid according to the following equation. Which one of the following changes will not affect the reaction rate? So putting the reaction mixture in a hot water bath, that's increasing the temperature, that will have an effect. Using the same mass, but of powdered magnesium. Now you're changing the state, it's going to increase the surface area, it's going to have an effect on the reaction rate. Option C, increase the volume of hydrochloric acid. Now, ordinarily, you would think that it's going to increase the rate, but they tell us that the hydrochloric acid is in excess, meaning if there is hydrochloric acid left over, then adding more hydrochloric acid isn't going to do anything because there was already some that's left over. So the answer here is C. Now question 1.6, which one of the reaction rate versus time graphs represents the reaction between magnesium and excess dilute hydrochloric acid? So again, it's linked to 1.5 in a way because it's the same reaction with the same excess hydrochloric acid. Now, the thing to understand is that at the beginning, you're going to have a very high rate. So it's going to start, so it's not going to start at 0 because the rate is going to be very high. You have a lot of molecules, a lot of magnesium, and it's going to be reacting. So from the onset, it's going to be very high. So B and D are out. So we're looking at A and C. Now, which one is it going to be? So A is basically saying that the reaction rate is not going to 0, whereas C is saying that the reaction rate is going to go to 0. So the answer that's correct is the answer C. And the reason why is because all the magnesium is used up. There is no magnesium left. And so the reaction is going to come to a complete stop, meaning the reaction rate is going to be 0. Now 1.7, which one of the following will not affect the equilibrium position of reversible chemical reactions? Okay, so temperature. So temperature, if you are doing Le Chatelier's principle, you will look at temperature, you will say you will look for what is the endothermic reaction, what is the exothermic, then that will be favored. If you're thinking about pressure, you are thinking about the number of molecules. If you're thinking about concentration, that's going to have an effect. The only one that does not have an effect on the equilibrium position, it just increases the rate, is the use of a catalyst. So 1.7, the answer is B. Question 1.8. The reaction given below reaches equilibrium in a closed container. The Kc value is 0.04 at a certain temperature. Okay, so we look at this reaction and we can see that forward reaction is exothermic. Which one of the following factors will change the Kc to 0.4? So what we want to do here is we want to get the Kc from 0.04 to 0.4. So we want to increase the Kc. Now how can we increase Kc? So remember, Kc is equal to the concentration of the products divided by the concentration of the reactants. So if you want to get Kc larger, you can increase the concentration of products, or you can decrease the concentration of the reactants. So either one, right? Now we go to the options and we look at A and B. So A and B is just there to throw us off. So A and B is going to be out. The reason why is because the only thing that affects Kc is temperature. So we're going to look at C or D. Now, what will happen if I increase the temperature? If I increase the temp, that's going to favor the endothermic reaction, right? So the endothermic reaction is the reverse reaction. So the reverse is going to be favored. That means the concentration of my reactants is going to go up. That means that's not what we want. We want concentration of reactants to go down. So if I increase the temperature, that's not going to be an option. So that means the only option left is D. So 1.8, the answer is D. Question 1.9. During a titration to determine the concentration of an acid using a standard solution of a base, the learner pipettes the base into a conical flask. The learner then uses a small amount of water to rinse the inside of the flask so that all of the base is part of the solution. How will the extra water added to the flask affect the results of this titration? Now, this is a question that they pose to try and trick you. So you would think that if you add H2O, you are going to be diluting. And ordinarily, yes. However, if you're thinking about what the learner is trying to do here, they are conducting a titration. Now, during a titration, neutralization takes place. The number of moles of acid will react with number of moles of base. If you dilute, you are not affecting the number of moles. The number of moles of the acid and number of the moles of the base are going to be the same, or they're going to neutralize one another. So by making the volume larger, you're not really affecting the number of moles. So you can think of it in that way, and so then the answer will be D, that the concentration is going to be the same. Another way you can think of it is if you look at the formula CAVA, so this is for a titration, over CBVB, that's equal to NA over NB. Okay, so think about the quantities that you have here. So you have the volume of the acid, right? That's given. So we know, well, that's not given, but they know it. They know the concentration of the base since it's a standard solution. They know the volume of the base since they used the pipette to dispense the base. They know the number of moles of acid. They know the number of moles of base. So they can easily calculate the concentration of the acid. The water plays no part in it. So the answer there is D. Question 1.10. Which one of the following statements is always true for monoprotic acids? Okay, so for A, the lower the concentration of the acid, the weaker the acid. This is not true. Okay, because the strength of an acid is dependent on the acid itself. It's an inherent property. It's an inherent property of the acid itself. So A is out. B, there will be more H3O plus ions in 100 cm cubed of a strong acid solution than in 100 cm cubed of a weak acid solution. So this is not true either, because if you have a low concentration of a strong acid, for example HCl, and you have a high concentration of a weak acid such as CH3COOH, both are classified as monoprotic, the number of H3O plus ions are going to be different. It's not going to be the same. C, the pH of a strong acid is lower than the pH of a weak acid. That's also false. And that's false because, again, it depends on the concentration. You can have a high concentration of a weak acid and have a lower pH. It is possible. However, the one that's not possible, the one that's not always true, is D. 1 mole of a strong acid will produce more H3O plus ions. The one that is always true, rather. Excuse me. 1 mole of a strong acid will produce more H3O plus ions in water than 1 mole of a weak acid. So this is always going to be true for a monoprotic acid. For example, HCl is a strong acid, and it is a strong acid because it will dissociate or it will ionize completely, meaning it's going to completely give away that H plus and that Cl minus. So for instance, 1 mole of your HCl will give you 1 mole of your H3O plus. However, for a weak acid such as CH3COOH, your acetic acid, 1 mole of this is not going to give you, it will not give you 1 mole of H3O plus. And that's because it is a weak acid, and weak acids will ionize partially. So the answer is D. 1 mole of a strong acid will produce more H3O plus ions in water than 1 mole of a weak acid. Question number 2 reads, the letters A to H in the table below represent 8 organic compounds. Okay, question 2.1 says, write down the letter or letters that represents the following. A functional isomer of compound G. Compound G, I'm seeing the double bond. I'm seeing the COC that tells me that it is a ketone. So G is a ketone. A functional isomer of a ketone is an aldehyde. So we are looking for an aldehyde. So we go through our options, and we are. I noticed that a CHO, like so. So C is an aldehyde. 2.1.2, a haloalkane. So a haloalkane, halo means halogen. So I'm looking for a bromine, a chlorine, or any one of those halogens. Remember, there's a few of them. So if I look at this, I can see A has 2,4 dichloro, and it ends in ane. So halo, halogen, and alkane. So the answer there must be A. 2.1.3, the letter that represents something that belongs to the same homologous series as compound H. So compound H is an alcohol. Butane 1-ol is an alcohol. So I'm basically looking for another alcohol. You look at A, no. B is not an alcohol. C is not an alcohol. D could be an alcohol because I'm seeing the CHO here. E is not, F is not, G is not, H is. So the answer is D. It is an alcohol. And the reason why it is an alcohol is, if you think about it, you have a CH2, so you have that bonded to a carbon, so that carbon right there is that carbon. That carbon's bonded to a hydrogen, and that's bonded to an OH. And then you have a CH3, like this. So answers in that order is C, A, and D. Question 2.2. Write on the IUPAC name of compound B. So compound B is this. I'm seeing a triple bond, so it's going to be an alkyne. Let's find the longest chain. So longest chain is going to be that one. Now think about the direction that we're going to number it. Remember, when we number, we need to give the triple bond the lowest possible number. So if I number from right to left, that's going to be 1, 2, 3, 4, 5, 6, and 7. If I number the other way, it's going to be 1, 2, 3, 4. So the way that we've numbered it now is correct. So this is going to be something, and we're going to have 7 carbons, so it's going to be hept. The triple bond is on carbon 3, so hept 3 ine. So that's what it's going to end in. Then if you want to look at the branches, so we have a methyl branch here, we have an ethyl branch here. So we have a 2-methyl, and then we have a 5-ethyl. Now all we need to do is put this all together. Remember, alphabetical order. E comes before M, so it's going to be 5-ethyl dash 2-methyl hept 3-ine. Question 2.2.2, the structural formula of compound A. So compound A is this 2,4 dichloro 3-ethyl 6-methyl octane. So I'm going to start with the octane. Octane meaning 8 carbons. So 1, 2, 3, 4, 5, 6, 7. I'm just going to add the 8th one here. So I'm going to have a 2,4 dichloro. So a chlorine on carbon 2, a chlorine on carbon 4. 3-ethyl, meaning an ethyl group on the third one. And 6-methyl. So that's 4, that's 5, that's 6 in methyl group here. And now we just draw in our hydrogens. So hydrogen all throughout like so. Quite a few hydrogens, but that's what is required for a structural formula. So hydrogens all over here. There, there, and there. Moving on, 2.2.3, name of the homologous series to which compound C belongs. So compound C, I'm seeing a 4-mile group. So this C double bond O bonded to an H, like that. That is unique to aldehydes. And 2.2.4, what is the structural formula of the functional group of compound G? So compound G, this is a ketone, since there is an oxygen that's between 2 carbons. So it's going to look like this. There's going to be a double bond O, there'll be a carbon to the right, and then a carbon to the left. So this is the functional group of compound G. Now moving on, question 2.3, consider compound D. Okay, that is the alcohol that we mentioned earlier. 2.3.2, write down the structural formula of the positional isomer of compound D. Okay, so compound D is this. So we have 1, 2, 3, 4. There's 4 carbons. There is an OH here. So they want the structural formula of the positional isomer. So positional isomer it's the same molecular formula, but the position of the functional group will change. Now, I can't move this functional group here, because if I move it there, then I'm just going to be numbering it from that way, and it's going to be the same thing. So the only option I have is to move this to the first carbon. So my answer here is going to be this. There's going to be an OH here, and then hydrogens all around like so. Okay, right. 2.3.3, is compound D a primary, secondary, or tertiary alcohol? So compound D, okay, here's compound D. Is it a primary, secondary, or tertiary? So remember, to figure that out, you look at the OH, right? The OH is bonded to a carbon, and that carbon is bonded to 2 other carbons. So because it's bonded to 2 other carbons, it makes it a secondary alcohol. And that we've given the reason already. The OH is bonded to a carbon that is bonded to 2 other carbons. Okay, moving on. Question 2.4 now. Compound E and H are heated together in the presence of a catalyst in a test tube to produce an ester. So E and H. So E is this compound here, that is ethanoic acid. Okay. And H is butane 1-ol. So butane 1-ol. So they want to know, name the reaction that takes place between a carboxylic acid and an alcohol. So 2.4.1, that is called esterification. 2.4.2, the name of the catalyst used, name or formula. So let's just go with the formula H2SO4. 2.4.3, what is the structural formula of the ester that is produced? So when you're drawing an ester and you've been given the reactants, first use the alcohol. So butane 1-ol. So we're going to have 1, 2, 3, 4. Then after this carbon, you're going to add something called cocoa bonds. So an O, then a C, then an O. So that's what we're looking for, cocoa bonds. Now, from this carbon onward is the carboxylic acid. So the carboxylic acid is ethanoic acid. There's 22 carbons. So if that's carbon 1, that's carbon 2. And we just fill in the rest of the hydrogens like so. So the first part is the alcohol. The second part is the carboxylic acid. And 2.4.4, what is the IUPAC name of the ester that is produced? So we name the alcohol first, butane 1-ol, so that becomes butyl, and ethanoic acid becomes ethanoate. Now question 2.5. The reaction below illustrates the complete combustion of compound F in excess oxygen. Okay, 45 grams of compound F. So I'm assuming compound F is this. Let's just confirm. Yes. Reacts completely with oxygen at standard temperature and pressure. If the percentage yield of carbon dioxide is 76%, calculate the volume of carbon dioxide that is formed. So to answer this question, first, we've been given the mass. So let's go ahead and calculate number of moles. So the number of moles of this compound is going to be the mass, 45, divided by the molar mass. If we add that up, you're going to have 5 times 12 plus 12, and that's going to give us 72. So that gives us 0.625 moles of C5H12. Now we do a mole ratio. So C5H12 to what we want CO2, from the reaction is 1 to 5. So if I have 0.625, I multiply by 5, I'm going to get the number of moles. This is going to be 3.125 moles of my CO2. Now, remember, they tell me the yield is only 76%. So 76% of that 3.125 is actually 2.375 moles. So we only have this amount of moles of CO2. Now from here, we can get the volume. So we can say that volume is equal to number of moles times molar volume, since this is at STP. So 2.375 multiplied by 22.4, and that's equal to 53.2 dm cubed of CO2. Question 3 says, students use alcohols A to C to investigate a factor that affects the boiling point of alcohols. They use equal volumes of each alcohol and heat them separately in water baths. 3.2 reads, what property of alcohols makes it necessary for them to be heated in a water bath? So alcohols, as you see in many cooking shows and things, alcohols are very flammable. So you cannot just heat them over a flame. So you have to heat them gently, and often you will use a water bath if you need to heat them up. 3.3. What structural requirements must the alcohols meet to make this a fair comparison? So if you look at each of these alcohols have the OH group attached to the terminal carbon. In other words, it's bonded to the last carbon or the first carbon, depending on how you look at it. So in other words, the alcohol must be a primary alcohol. Because if it has branches and so on, then that's also, the branches are going to affect the experiment. 3.4.1 write down the independent variable. So what is it exactly that the learners are changing in this experiment? So they are changing the chain length, or the length of the alcohol. So the length of the chain. For example, in the first one, there's 1 carbon. Second one, there's 2. Third one, there's 3. 3.4.2. Name of the functional group of these compounds. So they want to know, what is the name of the functional group of alcohols? So the functional group is an OH, and that is called a hydroxyl group. 3.4.3, write down the IUPAC name of compound B. So compound B, you have CH3, so something like that. You have CH2, and then you have an OH. So this is simply, you have 1, 2, 2 is eth, so ethanol. So 3.5, which one of these 3 compounds will have the highest boiling point? That's going to be C. And 3.6, why is that the case? That is because, remember, alcohols have hydrogen bonds. So all the alcohols will have H bonds, right? And they, to a lesser extent, they will have London forces. Now, one of the factors that directly affects London forces is molecular weight, or molar mass. Now, as we know, as the molar mass increases, the strength of the London force increases, or van der Waals forces. So an increased molar mass means increased London forces, or van der Waals. And if you have an increased van der Waals, you have an increased boiling point. So C has the largest molar mass, and so it's going to have the strongest intermolecular force of the 3, and so it's going to have the highest boiling point. Question 3.7. The boiling point of compound C is now compared with that of compound X. Okay? Besides the conditions used to determine the boiling points, give a reason why this is a fair comparison. Okay, so we can see here that these are not the same homologous series. This has an OH, and that's COOH. So we're not comparing that. It doesn't have anything to do with chain length either. So the only thing left has to be molar mass. So I'm assuming here that the molar masses are the same. Right? So if it's not the length of the chain, if it's not the same homologous series, it's got to be molar mass. And I mean, we can probably add up, but I'm pretty sure that it is going to be molar mass. 3.7.2, fully explain the difference in the boiling points of compounds C and X. So X has a higher boiling point, and they want us to explain why. So remember, a carboxylic acid will have hydrogen bonds, but it will have 2 hydrogen bonds compared to the alcohol, which has 1 hydrogen bond. So since this has 2 hydrogen bonds, it's going to have a stronger IMF. Therefore, it's going to have a higher boiling point. Now, of course, if you are answering this in an exam situation, you will write this out in full sentences, but this is just the idea. Okay, now let's look at question number 4. Question number 4 is the reactions question. So the flow chart below shows how alkenes can be used to prepare other organic compounds. The letters A to G represent different organic reactions. Okay, so when I answer a question like this, first thing I want to do is I like to write down like a little cheat note, if you will. And it goes like this. So a 1 to 1, meaning you're going from an alkane to an alkane, or something saturated to something saturated. That is called a substitution reaction. If you're going from a 1 to a 2 meaning an alkene, that is called an elimination reaction. If you go from a 2 to a 1, that is an addition reaction. This is my little note that I like to keep. So even if I don't know much about the reaction, even if I don't know, if I can't remember the specific conditions or the mechanism or anything, this is enough just to get me the idea. So 4.1, write down the type of reaction represented by C. So C is showing me, I'm going from but1-ene. So but1-ene is an alkene, so it is a 2 because it has double bond. And I'm going to compound 1. I don't know what compound 1 is. Now, if I look at my little note here, the only reaction that goes from a 2 to a something is an addition reaction. There is no other option that goes from 2 to something. So 4.1.1, C must be an addition reaction. So that must mean that compound 1 must be an alkane. It must be an alkane, right? So let's look at 4.1.2. Compound, so compound F. All right, so what is F? So to figure out what F is, we need to know what compound 4 is, and then we need to figure out what compound 5 is. Okay, so if I look at, if I try to figure out what compound 5 is, I can look at reaction G. So reaction G, I'm going from an alkane, which is a 1. I am adding Br2, and that must mean, remember Br2 is, it's usually a test. It's a bromine water test. So it's a test for saturation. So that means you are going from a 1 to a 1, right? So whatever 5 is, 5 must be saturated, right? So this must be a substitution reaction. So the cheat sheet does work. However, you do need to know a little bit about your reactions. Now, if we look at reaction A, I'm going from a 2 to a something. So 2 to something, there is only one option that goes from a 2 to a something. This must be an alkane or something that is saturated. So this must be a 1. So reaction F is going from a 1 to a 1, which must make it a substitution reaction. So again, I don't even need to know what the products are if I just figure out if it's going to be 2 to 1, 1 to 1, or 1 to 2. 4.1.3, reaction D. Reaction D is going from a 1 to a 2. 1 to a 2 is elimination. Okay, let's move on. 4.2, for reaction A, write down the IUPAC name of compound 4. So 4.2.1, I'm going from but1-ene. So I'm going from an alkene. I'm reacting it with water. So something with water. I'm going to a 1. Right? So this, as we said earlier, A, this had to have been an addition reaction, right? And if we are adding water to an alkene, we are going to be making an alcohol. So let's draw this alkene out. So but1-ene, 1, 2, 3, 4. There's my double bond. During an addition reaction, the double bond will break. So that double bond will break. You're going to get two vacant slots now, two vacant spots. So this has two hydrogens. This has one hydrogen. Now, when you are adding an alcohol, remember you are adding an H and you are adding an OH because you're adding water. So the H will go to the carbon with the most H's. So between the two, it means the H is going to go here. That means the OH will go here. So if you're going to name this, this is going to be butan 1-ol, or butan 2-ol. Sorry, butan 2-ol. 4.2.2. So let's write this down. This is going to be butan 2-ol. For reaction A, write down the name or formula of the inorganic reactant needed for this reaction. So of course you need water. So H2O. 4.2.3, what type of addition reaction is this? So they even told us that it's addition reaction. So you're adding water. If you don't have water and doctor tells you you need to have water, doctor telling you need to hydrate yourself. So this is a hydration reaction. Okay. Question 4.3. For reaction G, bromine water, here we go, is added to compound 1. So there we go, you are adding bromine water. Is compound 1 a saturated or unsaturated? Give a reason. So compound 1, we said it's an alkane. So 4.3.1, it is saturated. And why is it saturated? Because it contains only single carbon-carbon bonds. 4.3.2, write down the reaction condition for this reaction. So there's a few, but one of the most important ones is you need UV light. Okay, question 4.4. Write down a balanced chemical equation using structural formulae for reaction E. Okay, so for reaction E, let's look at reaction E. So reaction E is an interesting one. We haven't discussed that. So you have but1ene and you are adding HCl. So you're going to get something. Then that is undergoing reaction E, and you are making compound 3. You are also going to get NaCl and some other product. Okay, so that's an interesting one. Now, B has to be an addition reaction because it's the only one that goes from a 2 to a something. So this must be 1. So this must be an addition reaction. Now, if I think about what product I would have for compound 2, and they tell me it's the main product. During that addition reaction, and I'm adding HCl, two things will occur. So I'm thinking first, the double bond is going to break. And secondly, the chlorine is going to be substituted onto the carbon that has the least number of hydrogens. Because of course the hydrogen will go to the carbon with the most number of hydrogens. So compound 2 is probably going to look like this. So but1ene, so 1, 2, 3, 4. The chlorine is going to go here. Right? So just like the alcohol, very similar to the alcohol, where the OH was bonded on the second carbon. In this case, the chlorine will be on the second carbon. And I am surrounded here with hydrogens. Okay, now I'm not going to draw the hydrogens, but you can imagine for the sake of this example that there's hydrogens all around. And it is undergoing some reaction. Now, a clue that tells me the the reactant or another reactant that's going to be used is if I look at this right here, the NaCl. So the NaCl is telling me that I needed to have added something with Na in it. And now the most common reactant that you add with Na is NaOH. So if I add NaOH here, right, a few things are going to happen. First, the Na and the Cl are going to bond. So I'm going to get my NaCl, right? Then I'm going to have an OH. Well, this OH that's free. Now, OH just needs an extra hydrogen to make water. So a hydrogen is going to be removed. Now, if I have to draw this, let's draw this. So you have that right there. You have your hydrogens here. Remember, the chlorine was taken away. And now we are deciding on which hydrogen are we going to take. Remember, the chlorine was removed from here. So remember this, the rich get richer and the poor get poorer. So you are going to remove a hydrogen from a carbon that has the fewer hydrogens. So if I look at this carbon has 3 hydrogens, whereas this carbon has 2 hydrogens. So it's actually going to be this hydrogen here that's taken away and bonded to form your water, and a double bond is going to form here. And so my product is going to be this alkene, your NaCl, and your H2O. So those are my products. Now, let's move on now, I think, to the last question, question 4.5. For reaction B, write down 2 reaction conditions required for this reaction. Okay, let's look at it. Where's reaction B? Okay, so reaction B is this one here, the one that we spoke about, where you are doing an addition reaction. So when you are adding HCl, what's 2 things that we need to ensure that we have? Now here, there's no other way. It's easier if you just remember it. So you gotta just remember that there shouldn't be any water. No water. Because remember, if there's water, then there's a chance of forming an alcohol. So no water. Okay? And there is another one, which is that we must have unreactive solvent. So those are the 2 reaction conditions that we must remember. So question 5 reads, a student is asked to design an industrial process to produce sulfuric acid. One of the reactions in the production of sulfuric acid is the roasting of a metal ore that contains lead 2 sulfide. The student does a test experiment in which 36.8 grams of oxygen gas completely reacts with 800 grams of the metal ore. All of the PBS in the ore reacts, and only the PBS in the ore reacts with oxygen. 5.1.1 calculate the amount in moles of O2 that reacts. So I'll use the formula N is equal to mass divided by molar mass. The mass of oxygen that we've been given is 36.8 grams, and the molar mass of O2 is 32. That gives me 1.15 moles of oxygen gas. 5.1.2 calculate the mass of pure PBS in the metal ore. So here I'm going to do a mole ratio first. So the ratio of PBS to O2 is 2 to 3. So if I want the number of moles of PBS, I'm going to say 2/3 times 1,15, and that gives me 0,77 moles of PBS. Now I can calculate the mass by using N is equal to mass over molar mass. 0.77 is equal to the mass, which is what we want, divided by the molar mass of PBS, which is 239. The mass is then equal to 184.03 grams. Question 5.1.3. Calculate the percentage mass of the PBS in the metal ore. So all we need to do here is we'll take the 184.03 and we'll divide it by the total mass of the ore. So that's 800. And because we want a percentage, we multiply by 100, and that will give me 23%. Now let's take a look at 5.2. In another experiment, 50 grams of sulfur trioxide reacts with water. The amount of sulfur trioxide present in the container is monitored over time. The following graph is plotted. So 5.2.1 reads, write down the formula of the limiting reactant. So the limiting reactant is the reactant that is used up in a reaction. We can clearly see from the graph that's given to us, SO3 is not used up. There is SO3 left over. So the SO3 must be the excess, and that must mean that the other reactant, which is H2O, that must be the limiting. Five point 2.2. At what time on the graph was the reaction rate the fastest? So we have options here, 2, 4, and 6. So we can answer this by looking at the steepness of the curve. So at 2, it's quite steep. Then it tapers off at 4, and then at 6. So you can see that the gradient here is the highest here, and it is the lowest here. So the highest gradient will indicate the fastest rate, and the lowest will indicate the lowest rate. So if they wanted to know when was the reaction rate the fastest, it was at 2 minutes. 5.2.3. What happened at 6 minutes? So at 6 minutes, you can see that the gradient is the lowest. Actually, it's now a horizontal line. And that will occur when the H2O is used up. There's no reaction taking place. In other words, the reaction is now completed. There's no rate. So a few things you could write here. You could write that the reaction has stopped. You could say the H2O is used up, or both. Question 5.2.5. Calculate the rate of the reaction in grams per second during the first 2 minutes. Okay, so first thing is they want it in grams per second, so we need to convert the time. So 2 minutes is 120 seconds. Now let's get coordinates. I'll clear this up. So at 2 minutes, the mass is 25 grams. So this could be, instead of 2 minutes, I'll write 120 because that's the seconds, and 25. And at the start, it's 0 seconds and 50 grams. So if we want to calculate the rate, we're basically calculating the average gradient. So what is the average gradient between these two? So it'll be 25 minus 50 divided by 120 minus 0. And that's equal to minus 0,208 grams per second. Though we won't leave our answer as negative, we'll leave it as positive. So the answer is going to be 0,208 grams per second. Let's take a look at question 5.2.6. 5.2.6 says copy the above table or graph in your answer book. On the same set of axes, use a dotted line to show the curve that will be obtained when the temperature increases. So basically, if you increase the temperature, the particles are going to have more kinetic energy. There's going to be more collisions. And that's going to increase the rate. So what we're looking for is a steeper curve. So I'm going to use a different color. Let's use red. So at the start, it's going to go down, steeper, and it's going to flatten much earlier. So something like that. Question 5.2.7, in terms of collision theory, explain why, excuse me, explain why the rate of a chemical reaction increases with increasing temperature. So we've explained it already here. So this is 5.2.7 as well. Let's take a look at question number 6. So question 6 reads, nitrosyl chloride, NOCl, is a yellow gas that decomposes into colorless nitrogen monoxide and green chlorine gas at temperatures above 100 degrees Celsius. Consider an equilibrium mixture of NOCl, NO, and Cl2, which is initially yellow-green in a sealed container. So 6.1.2, NO is added to the container at constant volume. What color change will be observed in the container? Explain the answer. So if you add NO, and according to Le Chatelier's principle, the system will want to decrease the amount of NO. That means that the reverse reaction is going to be favored. And that means that it's going to appear yellow. Question 6.1.4. When the pressure in the container is changed, the color becomes green. Use Le Chatelier's principle to explain whether the pressure was increased or decreased. So, in other words, if we're talking about pressure, we are talking about number of molecules. If it's green, it means that the forward reaction was favored. The forward reaction would be favored if the system is favoring more molecules. Because if you look at this side, you have 2 and you have 1. So it's favoring more molecules. It's favoring, in other words, a high pressure. That means the pressure must have decreased. Now let's go through it once more. If the pressure decreases, the system will want to increase the pressure. It's going to favor the side with more molecules. That's the forward. So that's why it's going to appear green. Question 6.2. The Haber process uses nitrogen and hydrogen gas to produce ammonia represented in the reversible reaction below. The Haber process was researched. The graph below shows how the percentage yield of ammonia is affected by changes in temperature and pressure. Okay. In industry, the Haber process is typically operated at a temperature of 250 degrees Celsius and a pressure of 200 atmosphere. 6.2.1 is the forward reaction in the Haber process, exothermic or endothermic. Okay, so to answer this question, I'm going to assume something. So I'm going to say, here's my reaction, N2 plus H2 gives me NH3. And that should be 2, that should be 3. Now I'm going to assume delta H is greater than 0. Let's assume it. Just to assume it, and then we'll see what happens. So if I increase the temperature, right, the endothermic reaction is favored. That would mean that the forward is favored. Therefore, I should get more NH3. That's what we should get. Let's look at the graph and see if that's the case. So it starts, it's at, well, they tell us 250 degrees Celsius, so 250 is here. So this is where it normally operates at. If I increase the temperature, let's say I increase the temperature to 300, what happens to the amount of ammonia that we have? The amount of ammonia at the same pressure decreases. So this is not going to work, and that's because the delta H must be the delta H must be less than 0. It must be an exothermic reaction. And the reason again is because we can see from the graph that when we increase the temperature, we had less amount of NH3 being produced. If the reaction was endothermic, you should have had more NH3 being produced. So again, answer is exothermic. 6.2.2, explain the answer. So, okay. So we'll say, from the graph, we can see that an increase in temperature resulted in less NH3 being produced. That must mean that the delta H for the reaction must be less than 0. And we have to use Le Chatelier's principle here. We'll say if you increase the temperature, the system is going to favor the endothermic. So the endo is the reverse reaction. That means you're going to have less NH3, which corresponds to what we're seeing in the graph. 6.2.3, well, 6.2.3. What is the percentage yield of ammonia at 250 degrees and 200 atmosphere? So 250 degrees and 200 atmosphere. So here's this curve. We're following this curve here. We're reading it across. It's 50%. Now let's take a look at question 6.3. A solution is prepared by dissolving 4 moles of CuCl4 2- completely in water to make a solution of volume 2 dm cubed. When equilibrium is established, there are 2.2 moles of CuH2O6 2+ ions present at 25 degrees. So we've been given the reaction. determine the value of the Kc for this reaction at 25 degrees. So here we'll, as always, use a rice table. So R, I, C, E. So let's construct this table. Now, we will not consider H2O in this rice table because H2O is a liquid. Yeah, it's pure liquid. So its concentration isn't going to fluctuate or change. So I will draw in here CuH2O 6 2 plus, then 4Cl minus, and I'm going to use a double line here just to separate the reactants products, and then I'm going to have CuCl4 2 minus. Now R stands for ratio. We'll fill in the ratio of the reactants and products. So Cu, there's a 1 here, so 1 will go there. There's a 4, so 4 will go here. There's a 1 here, so 1 will go here. They tell us that a solution is prepared by dissolving 4 moles of that. So there should be 4 here. Completely in water to make a solution of volume 2 dm cubed. So we'll put here volume is 2. When equilibrium is established, there are 2.2 moles of CuH2O. So at equilibrium, you have 2.2 here. All right. So we have a lot of information actually. What we can do is we can say that if we started by including this, that means there'll be 0 here and 0 here. So what's the change? So the change here is it's increased by 2.2. Now we do a ratio. The ratio here is 1 to 4. So this will increase by 8.8. So that means at equilibrium, you'll have 8.8. Now this side will have a minus. That's why I put like a double line to separate it. And now we use the ratio. The ratio here is 1 to 1. So if that increased by 2.2, this will decrease by 2.2. So this will be 1.8. So we have all of the equilibrium moles now, and we just need concentration to calculate Kc. So let's add another row. We'll add a concentration row here. To get concentration, all you need to do is divide by the volume. So 2.2 divided by 2 is 1.1, 8.8 divided by 2 is 4.4, and 1.8 divided by 2 is 0.9. Now we can calculate Kc. Kc is equal to concentration of products. So product in this case is the CuCl4. It has a concentration of 0.9. So 0.9 to the power of 1 divided by my reactants so this one is 1.1 to the power of 1, and here 4.4 to the power of 4. That gives me an answer of 0.002. No units because it's Kc. Now let's take a look at the last question of the paper, question number 7. Question 7 reads, consider the following balanced equation showing some acid-base reactions. So we have A and B. We'll go to 7.2. Consider the chemical equations A and B above. 7.2.2 says, write down the formula of an amphoteric chemical substance other than H2O. So an amphoteric substance is something that can act as both an acid and a base. If I look at A and B, I see that this substance can act as an amphoteric substance. It can donate a proton, it has one to donate, and it also can accept a proton because it has a negative charge. So HSO3 minus. 7.2.3. Write down the formulae of the conjugate acid-base pairs in reaction B. So in reaction B, the conjugate acid-base pairs will be H2SO3 and HSO3 minus, then H2O and H3O plus. So 7.3, which indicator must be used in reaction A? Choose from methyl orange, bromothiamine blue, or phenolphthalein. Give a reason for your answer. So if you look at reaction A, you can see that you have HNO3, which is a strong acid. You have KOH, which is a strong base. And so the salt will be a neutral salt. So we need to choose an indicator that will have more or less sensitivity to a neutral range. And the answer there is going to be bromothiamine blue. Because again, it is sensitive to a pH range of about 7. 7.4, consider the reactions A and C shown below. A 13-gram impure sample of KOH is initially dissolved in 200 cm cubed of a 1.2 mol per dm cubed nitric acid solution. Okay, the nitric acid was in excess. Assume that the volume remains constant. 50 cm cubed of the resulting solution was then titrated to neutralization using 23.67 cm cubed of a standard 0.85 mol per dm cubed sodium carbonate solution. So that's reaction C. 7.4.1, determine the amount of nitric acid that was added to the KOH. Okay, so here we'll just do N is equal to CV. So the concentration that they've given us is 1.2. The volume is 0.2. We have to convert that. So that is 0.24 moles in total. Right? So remember that this 0.24 moles is going to be used in reaction A and reaction C. So 50 cm cubed of the resulting solution was then titrated to neutralization. Okay, so that's reaction C. 7.4.2, calculate the percentage purity of the KOH. So to calculate the percentage purity, what we have to do is we have to work backward. So we'll start by figuring out how much was used in reaction C, and then we'll work out how much was used in reaction A, and then we can calculate the percentage purity. So let's start with reaction C. So in reaction C, we know the concentration and the volume of the sodium carbonate. So for sodium carbonate, so Na2CO3, we can calculate number of moles. Number of moles is equal to CV. So 0.85 multiplied by, so we need to convert that, that's 0.02367. That gives us 0.021195 moles. Now we do a mole ratio. So you have HNO3, so it's 2 to 1. So to get the number of moles of the HNO3, you multiply this by 2. So this is going to be 2 times 0.02011195. And that's equal to 0.040239 moles of HNO3 that was used in reaction 3. Right? But we must again remember that this was in 50 cm cubed. In 50 cm cubed. The original sample was in 200 cm cubed. So we can't compare them yet. So what we need to do is we multiply. So to get from 50 to 200, you multiply by 4, and then you multiply this by 4 as well. So we'll say in 200 cm cubed, you're going to get 4 times 0.040239, and that gives you 0.160952 moles. So that's the amount that was used in reaction C. So 0.160952. So if we know how much we started with, we know how much was used in reaction C. If we subtract these, we can work out how much was used in reaction A. So in reaction A, it'll be 0.24 minus 0.160952, and that gives us 0.079044 moles. Now that we have the number of moles that was actually used in reaction A, we can do a mole ratio. So let's go forward here. So the mole ratio for HNO3 to KOH is 1:1. So therefore, you're also going to have 0.079044 moles of KOH. Now from here, we can calculate the mass. So the mass is going to equal 0.079044 multiplied by the molar mass of KOH, which is 56. And that gives us 4,426464 grams of KOH. Now to calculate the percentage purity, we take this grams, so 4.426464 divided by the amount that you started with, 13 times 100, and that gives you 34.05%.